And the examples are new, so.
You want to be recorded?
It's fine by me.
Don't mind being recorded. All right, hi everyone. From here, we're very happy. I can't say we're very own Ian, but someone's very own Ian. So Ian has done lots of amazing work on catalytic space computation. We usually don't go through a long bio, so I will just say that it's some cool things. Some of you might have seen we had a reading book. We spent 6 months trying to understand 2 or 3 of his papers and what they meant. So yeah, we're very happy to have him here. Tell us more about what is happening with. I should have not used the word catalytic if you wanted to say this, but I spoiled it. So okay.
No. It's all good. This is just the hook. All right, yeah. Thanks for coming out. I'm still amazed that this is my first time in Waterloo since I spent 6 years down the road in Toronto. I didn't know there could be, better places in Ontario than Toronto, but here we are. So, I tried. Yeah, so I'm going to be talking about stuff related to using full memory, catalytic space, etc. So how many people here were part of Sophera's reading group, course, etc.? Okay, so I'm preaching to about half the choir here. So I'll recap stuff at the beginning, just in case. And this is the 2026 edition. So if you've seen this talk multiple times before, I sort of apologize, but also hopefully you will see some nice examples that are relevant to the current day. So we're going to start with the reason that anyone cares about this nowadays, which is time and space. The boring one. So we're going to be talking about the relationship between time and space. And as we all learned in grade school, we have this class time t, every function computable in t steps, and space s, that's still a typo, every function computable with at most s bits of memory. And we know a nice relationship between them, which is that space t is sandwiched in between time t and time 2 to the t. This side because, you can only touch t bits of memory, and this side because there's at most 2 to the t configurations of your memory, and if you repeat, we assume you're in an infinite loop. We also have hierarchy theorems, which tells me that more time is more space, and so one of these two is not an equality. We don't really know which one. With an asterisk, we actually did already know that there was a little separation here, like a log separation, but we didn't really substantively know which of these is not an equality. And so we could study either question. We could try and find a function that's in space t, but not in time t, or we could try and find a function which is run in time 2 to the t, but not in space t. And we're going to aim for this latter one. So think, if this is too abstract, think polynomial time versus log space. We want to find some separating example. And in fact, that was exactly what was proposed by a number of authors back in 2012, a function that is in time 2 to the t, but requires space way bigger than t. They proposed a function which, these slides were designed for a more general audience, but if you've seen tree evaluation, this is what we're talking about. It has some obvious algorithm, which takes time 2 to the t, polynomial time, or even linear time, but the space is like t squared, log squared f. And they conjectured that this obvious algorithm really is the best that you can do. So that's what you need to show, that this obvious algorithm is really space optimal. And it turns out that there's some flexibility in what the obvious algorithm could do. So you have to prove a bunch of trivial facts about, nothing's trivial in this field, trivial facts about how the obvious algorithm even manipulates its space. You can take the same structure, but you need to prove that it uses space in the way we expect. Of course, in order to prove any of this, we started with toy cases, n equals 2, 3, 4, etc. And I don't even think we made it to 4, but there was a vigorous line of work coming out over the years. So fixing, essentially assuming away this trivial facts problem, you can say some stuff over here, or again, for small examples. So I say, trivial facts, nothing is trivial in this field. In fact, it turns out that sometimes you need to look at your trivial facts, because we're going to analyze one such fact now, which is, imagine you have the following 2 tasks to perform. The first task is you have to compute some function f, which requires some amount of space. And let's say this is known to you. It is space f. And the second thing is you have to remember some string z. Now, this is space z. For most, if I give you like a random z, for example, this is just the length of the string. But OK, let's just call it space z. Third task, do both at the same time. I have a string z I want you to remember, and I have a string function f I want you to compute on some external input. So if you want to perform both of these tasks, we'll call this the space of f and z. And the question is like, are these two things equal? Is it the space to actually compute f while remembering z equal to the sum of the two? And a related question, not quite the same, but morally very similar, is consider the following two scenarios. Option 1, you have access to some small amount of memory. And for option 2, you have some small amount of memory plus a whole bunch of extra memory. This is the string z, which is already filled in with some string that must be there when you finish the computation. So you can do some garbage to it in the meanwhile, but you can't really erase any of its information. And again, if you think this is a random string, like you really can't lose any information about this. And the question is just, is there any function that I can do in option 2 that's not doable in option 1? Just to drive home like how weird this question is, you can imagine your computer runs out of memory, and in order to satiate it, you're going to plug in something that's completely and utterly full, and yet somehow this aids your computation. And a priori, we thought the answer was no way. You've seen the title of the talk. You already know it's coming. This is completely false. It turns out for many functions f and every string z, the first thing I said is just not true. You can compute f while remembering z in way less space than it takes to do both tasks individually. And similarly, there is a whole host of functions for which we have no idea how to prove them in low space. But in this second scenario where I slap on a whole bunch of full memory, suddenly I can prove to you that I can solve this thing, no matter what's in the memory. So full memory does provably add quite a bit of power. And this throws a wrench in what we were trying to do. It means that one of the facts that we had staked this whole thing on is just not true. So now we have to work around this and come up with some other way of proving that the obvious algorithm is space optimal. And if you've taken some pairs course, you already know the punchline of this, which is that this fact alone was enough to sink the whole thing. It turns out the function they proposed is way easier than t squared space. It can be done in space only t times log t. And so this really undermines what we were trying to do. I mean, you could still prove that this is optimal, but we no longer have any intuition about why this thing should be a hard example. What was even funnier is that we started with this goal of separating time and space. We lost our candidate for doing so, and we managed to separate time and space in the opposite direction. So utilizing just this fact, Williams generalized this algorithm, which was due to Cook and myself, and showed actually the other side of what we wanted to show holds, that space t requires provably quite a lot of time. This is strange. We started with a lower bound, a very general lower bound. We narrowed in on one specific function. We got an upper bound for that function, and then we regeneralized that outwards to get a lower bound in the direction we weren't even looking. So this was a pretty big twist. And the even crazier twist is that the in-between of these two is another upper bound, which is that from this one function that's computable in space efficiently, we can prove that every time-efficient function can be computed space efficiently. And what makes this really surprising is not just the fact that this is a generalization, but like we started off with two facts about time and space that we thought were going to be quite difficult to prove. We had an angle on one. We ended up proving the one where we didn't think we had an angle, and we proved it via something we didn't even believe was true in the first place. So the whole thing has been kind of a roller coaster. But the upshot of it is that from this one fact about what full memory represents, we can derive pretty far-reaching statements about time and space. So it seems like this whole thing about reusing memory is like a solid component of our understanding of memory. And so we're going to ask in this talk, what can you actually do with a full hard drive? So we have to rig up the actual setting in question. And this is this catalytic computing framework that that was spoiled at the beginning of the talk. So this was introduced by Berman, Cleve, Hotsky, Laughlin, Steelman. We have one in the audience with us today. And this was that, so we take the typical space-bounded scenario, Turing machine. You have a read-only input tape of n bits. I really insist on read-only because we're talking about space. You have some output. It's 1 bit, so I don't really care if it's read-write or read-only, or write-only, but for larger outputs, you could think of this as like not counting as your memory. You don't get to win it. The whole read-write operations, the whole body of the computation happens in some space S work tape. And this is the space S class. We saw this at the beginning. Our new bolstering of it is going to be that we have C additional bits of memory, which we call the catalytic memory. And this is exactly the thing I said before. It's read-write, but no matter what initialization I give to it, you have to reset to whichever one I give you. So it's already filled in. You have no control over this, and you have to reset it while getting the output of the function, no matter what the input is and no matter what the catalytic tape is. And I'll just do a quick side. This is called catalytic for chemistry-related reasons. A catalyst is something that ends up exactly the same at the end of a reaction, but the reaction couldn't have occurred without it. So think of this as an analogous type thing. We're going to specify for pretty much the whole rest of the talk some specific parameters, which is my free memory is going to have like log n bits. This is log space. And my catalytic memory is going to be polynomial in length. So way, way larger than my main memory. But still, a priori, the question was, does this do anything? Like, it doesn't. If I didn't tell you, I guess the first time most people see this, they assume that this is just not a useful resource. Turns out that that is very far from the truth. So what is trivial is that this catalytic log space class falls between log space and polynomial space, right? It's log space with additional resources, so this part's easy. And if I didn't give you this resetting condition, then you would have p space. So, p space is a more relaxed version of CL. What they showed in the first paper is improvements in both directions. So all the way up from p space, we can reduce down to randomized polynomial time. And not just randomized polynomial time, but what's called zero error. So you'll never get a wrong answer. You'll only ever fail to output sometimes. And this is, in particular, this is in NP, for example. This is well within p space. It's widely conjectured to be equal to p. And so we've reduced all the way from polynomial space to polynomial time. But the nice part is that on the other side, we can show a whole bunch of nice functions which are computable. So for the complexity people in the audience, this is log depth threshold circuits. But if you care about specific functions, we can do things like estimating random walk probabilities, testing if two nodes are connected in a graph, computing the determinant, a whole bunch of things that we have no idea how to do in log space. And there were some improvements on both ends. There's a partial de-randomization of this. I'm not going to go into quite what that means, but it's a little bit better than just using random coins here. And on the flip side, we can do stuff like bipartite matching, linear matroid intersection, etc. At the end, I'll talk about the state in 2026, where I'll say a little bit more about this. A nice alternative proof of this was provided recently by the people who put it in log depth threshold circuits. This was not their motivation, obviously, but I should mention it. What's the knock-on effect of this is that if you believe complexity theorists, who I don't know how good their track record is at conjecturing, but if you believe them, then CL is strictly between these two. And that's a kind of nice fact, I would say. You're looking suspicious about this. Yeah. No, I mean, we have a world in which CPP equals exp. So yeah, we got nothing. All right. I think the bulk of the talk, I'm going to be talking about the two key ideas that we lean on everywhere in catalytic computing. And here is where, if you've seen this talk before, I'm going to give 2026 related examples for this. So, stay tuned. The two big ideas that we use throughout catalytic computing are compression and reversibility. So I have to clarify what both of those mean. Let's start with compression. compression is like the most obvious thing you would try and do if I told you, apropos of nothing else, no theoretical guarantees, no nothing. Hey, here's a thorough hard drive. You can use it however you want. I just want it back afterwards. What's the first thing you do? You try and compress it. And maybe that works. And maybe you free up a whole bunch of memory. And now all these questions are obvious. You run your favorite p-space, polytime, whatever. But this has to work for every tau. And as you all know from information theory, even saving 1 bit on average is like pretty much not going to happen. And that's assuming you have like perfect compression schemes. So this one is not going to help. Except that in this scenario, there is something slightly more we can say. It's incompressible, which means it's incompressible. Like, incompressibility is not nothing. And I've actually, just to spell this out right up front, if it's incompressible, then the nice thing that we can assume about it is that at least to our prying eyes, it is random. And this brings us to the paradigm called compressor random. You can think about this in theory. You can think about it in practice. Either way, you take your catalytic tape and you shove it through a compression scheme. Either a bespoke one tailored to the problem at hand, or just pull something off the shelf. And what you can say is that if you succeed in compressing, you suddenly have access to more free space, which is the only thing you really wanted anyway. So this is a very good scenario. But in the bad scenario, we still get access to something, namely a string that looks random. Now I put random in quotation marks. Why? Because it is specifically random with respect to whatever compression scheme you have. Right? Your compression scheme can detect no patterns that it can push down. And so in the theory world, oops, I lost the slide here. In the theory world, what's important here is that we need to design a compression algorithm and its decompression pair, of course, that work in CL. We can't go to some higher class to compress my tape. I have to work within the resources I've been given. And furthermore, in this failure case, in the success case, you have to prove that access to more free space is enough to compute the function. If you don't have that, then don't even bother with this, because if I gave you your entire catalytic tape free and you still can't solve the function, you should be doing something else. So I'm going to assume if you have access to more free space, you're good to go. On the flip side, I need to prove that if you fail to compress your catalytic tape, that you can deterministically, surely solve your function. And that's why it's important to design specific compression schemes with respect to the problem at hand. My example for today, although there are simpler examples, the one that has come up in the last half a year or so is computing matchings. And we are going to do this via the isolation lemma. So the isolation lemma says something stronger than what I've written here, but I will just say it for our purposes. It says that if I have a graph, say a bipartite graph, and I want to find a matching of maximal size, it turns out if I put random weights on the edges, sorry, I didn't say what the universe here is, say weights between 1 and n to the 5th or something like that. If I pick random weights for the edges, then for any k for which there is any matching, there is a min weight matching which is unique. So there are no two matchings which both have the same minimum weight in the graph. And the reason that they proved this in the context of matchings is that if this is the case, you can essentially, with some gadgetry and whatnot, compute what the maximum k is for which there exists a matching using just some determinantal calculations. And in particular, you take a matrix which has, you exponentiate the weights for every edge, and you leave 0 for every non-edge. It turns out that if you just analyze this determinant, what you get is the sum over all matchings of some plus minus 1 term based on whether the matching is even or odd as a permutation, times 2 to the weight of the matching, which is the sum of all the edges. And the nice thing here is that if the min weight matching is unique, then this thing has a low order bit which you can never mess with, right? If I didn't have this guarantee, then this plus minus 1 might screw me up and I might get 0 even if there exists a matching. But if there is a unique min weight thing, then this will surely be non-zero. And that's the big trick to computing min-weight matchings, or to find out whether or not there exists a matching of size k. Sure. Just think of them as numbers between 1 and n to the 5th. No, I mean, actually, I guess like the more degrees of freedom I give you, the more likely it is that there's a unique min-weight matching, right? I think I just need bit complexity, which is actually, I'll show you what the bit complexity is on the next slide. But after that, you can do whatever you want. I guess when you exponentiate, it gets a little bit, maybe it's fine. I guess there's no problems. Oh, Molmole, Vazirani. I guess before that, there was something by what? Valiant Vazirani, relating to polynomial time. But this is like I guess this is the most quoted result. This is the first one for matching. And this is where they like really spelled out this version of the isolation lemma. There are a bunch of nice proofs of this, which get different parameter regimes. Here's a really simple proof of it. Imagine I have two matchings, both of min weight of size k. Look at an edge that's in the first one, that's not in the second one. I can actually describe the weight of this edge via two quantities that have nothing to do with it. The weight of this edge is like the weight of the second matching, minus the weight of the first matching sans the edge. And of course, this means that you can describe the entire weight function with like slightly fewer bits. And assuming you can describe M1 and M2 very succinctly, which we do in our paper, like there's in the proofs of the isolation lemma, they have some different rigging up. What's important for the catalytic world is essentially that we show you can recover both M2 and M1 as long as you know that there's unique matching, a unique min-weight matching of one less size. So like if I've guaranteed that the min-weight k-1 size matching is unique, then if that's not true for size k matchings, I can actually carry out this argument. That's like where we came into the picture. But the point is just that this certifies that a random weighting scheme actually doesn't only has one unique min-weight matching, because otherwise you can compress. And that's an existential statement. We're going to reg it up as an actual like operational statement.
It's a random weighting, so is there some probability associated?
Yeah, there is. So I said you have to describe M2 and M1, right? So in particular, the only thing you end up needing to write down is like what are the endpoints of the edge? And maybe you have to write down k as well. So think of that as like 2 log n or 3 log n bits. So this compression only holds if the weights have at least 3 log n bits in them. So in other words, as long as your weights are randomly picked for some larger amount, then this holds with high probability, but the probability is related to what's the probability you can compress, right? Because it's possible you pick a random string that is compressible. So the bigger the range you make the weights, the more likely this statement holds. Yes, this is missing with high probability inside of it. Sorry, I should apologize. I'm just very used to giving board talks, and I forgot to check until yesterday. So there's a little bit of slapdashery coming here, but feel free to ask me anything that's not on the slide. All right, so how are we going to do this in a catalytic world? Well, I'm going to section off my catalytic tape into 3 pieces. Over here, I'm going to have W, which is going to be easily, is going to easily relate to our task at hand. Over here, I'm going to have det. What you should think of this as just working memory, where I do determinant calculations. And in the middle, I'm going to call this spare W for reasons that will hopefully become apparent later.
If you're this kind of bring back the start around the one before, like when you talk about MVP. I mean, this is only true if you have a perfect matching. Otherwise, the determinant is 0.
You can rig up. You rig up basically for every. If you give me k, I can add a bunch of extra vertices, like n minus k vertices, which match to everything on the left and right with a biclique, and I can actually set those weights deterministically without randomness. So yes, it's true. Like it depends on the k. I have to do a little gadget thing, but morally speaking, it reduces to a determinantal calculation. Yeah, thanks. Good. So the big takeaway here is that a random weighting allows us to compute matching as long as we have access to determinants, and a not good enough matching is something that is we can sort of recover the reason why it's not a good weight scheme, as long as we can as certified that at one level down we are good to go. Those are like the big takeaways at this point. And so now what we're going to do is we're going to actually show that all of this gives us a catalytic algorithm. So the first thing is I wrote down W here, and that's because I'm literally going to take my first n squared times 5 log n bits of my catalytic tape and treat them as a weight function. You know, n squared edges, or it's n choose 2 edge weights to fix, and 5 log n because, again, I want them to be in some range like n to the 5th. Now, I'm going to start with k equals 0. In other words, you know, a matching of size 0. And I'm going to assume that I have a unique min-weight matching of size k. For 0, this is just trivial. There's nothing. And you can construct nk using determinants. Here you can construct it using absolutely nothing. And I'm going to now ask, how many min-weight matchings are there of size k plus 1? And I'm going to split into 3 answers: 0, 1, and anything else. So if I only have one min-weight matching of size k plus 1, then I'm great, right? Like I've isolated, my weight function has been random enough to isolate not just size k, but size k plus 1. So I'm going to increment k and just go back here. Construct, you know, now I can construct that matching using determinants, and I can continue on my way. Now, how about 0? What happens if there are no min-weight matchings of size k plus 1? You're done. If you have no min-weight matchings of size k plus 1, then you have no matchings of size k plus 1. And so the answer is k. You return k. If you want to do the search problem, return the matching mk, which you can construct using determinants. So you can even find a matching of size k. It happens to be the min-weight one. Anyone would have been fine, but this is the one we know how to construct. And the greater than or equal to 2 case is the interesting one. This is where we need to do something with the fact that the weight function is not good. Remember, this just came from our catalytic tape. Like, what is the guarantees that this thing is random? We have no guarantees. It'd be great if it was. You know, the first 2 cases serve that purpose. Then the third case, we need to use the fact that it's not very random to compress. And I've already told you essentially what's going on there. There is some edge that's in M1 and not in M2. There's a further restriction, which is that this edge also isn't in the best weight k size k matching. You can prove that such an edge must exist. And then I told you on the previous slide that as long as I can construct the min-weight size k matching, which as long as I don't erase an edge in that, I can still do using determinants. Obviously, deleting an edge is not going to spontaneously make a better weight size k matching appear. But using these facts, I can actually compress. This weight WE is going to be redundant because just by knowing k and say where the edge appears, I can construct mk and I can use it to construct m1 and m2. That is the guarantee. That is what we did all the work in the paper to prove. It's not particularly difficult, but I'm not going to talk about it today. Great. What happened? Oh, it got smaller. So I can just erase it. Yep.
So like you still need to know where the edge is, right?
Correct. So you need to write down U, V, and K. Right? The edge is U, V. The level at which it happens is K. I have to write down those 3 log n bits, but in exchange I gain 5 log n bits because that's how many bits were in each of the weights. So it's true. I haven't drawn U and V here, but the point is I've freed up 2 log n bits, which I can just set to 0. And here's why I called it spare W. I'm going to move this 0 to the end for later use. And I'm just going to snatch a piece, like the last chunk of spare W, and move it over here, right? This is going to be a new weight, and this is going to induce a totally new weight function Not totally new, it's only different by one thing. But nevertheless, I no longer know what the min-weight matchings are going to be of all the smaller sizes. So just to be on the safe side, I'll completely start over. I will write down the fact that I have compressed once, keep track of how many times I've compressed, but I'll basically just start from scratch, reset k to be equal to 0, and I will start the whole process over again. In this process, I have freed up 2 log n bits. I put enough spare W here that I can carry out this procedure as many times as I need. I can keep doing this and doing this and doing this. If at any point I actually do, I am good to go, then I can return k. And if I fail to do so for enough steps, then I want to do something else. So in particular, at every step after I've compressed, I'm going to ask, how much have I compressed? If I've freed up enough, if I haven't freed up enough zeros, that's when I'm going to go back into the loop. But the moment I've freed up enough zeros, I just run a polytime algorithm for matching. I have a huge chunk of zeros, and I know very good algorithms for matching. I could have run a p-space algorithm here. But what's nice about this is, of course, everything has happened in polynomial time so far. So once I've done that, I can just run a p algorithm for matching and get the best k, get some k, etc. And I've done everything except, of course, I can't actually return k in either of these cases. I need to do the work of decompression. Now, I, again, am sweeping this under the rug. I have told you that decompression can happen because I can reconstruct from k, u, and v what the weight of it was. And so you have to unravel things. You have to go back one step at a time, like get back the last weight you compressed, then get back the second to last weight you compressed, and so on and so forth. And if you just run this backwards, again, a polytime procedure, you can eventually get back exactly all the spare w's that you had before, the original weight function. This det was always, was never perturbed, and so you're good to go. And that's the end of the proof. So this is how you take a randomized statement, like the isolation lemma, you turn it into, this is, by the way, what I meant by when I said earlier, there's a half derandomization or partial derandomization of CL in ZPP. So ZPP says, if you give me random bits, then I can solve CL. What the actual thing we can prove is, and what this shows, is that if you don't give me random enough bits, I can actually certify that fact using a compression scheme. As in, any time that I cannot efficiently solve my CL function in ZPP, it's because the random string is not just not random enough, but actually compressible. And so this is like where a lot of the arguments come in CL, because the moment you can give me such a compression-decompression scheme, I have a general template for how to solve other functions. All right, this is our first main technique out of the way, and that was a lot. So I'm going to stop here for either questions about what we saw or general questions about how to apply this framework elsewhere. Yes?
You're checking whether the compression worked. So you leave the catalytic data on the tape, and how do you do that? Do you need them?
How do you test like this greater than 2 case?
So you take the compressed string, and then you gotta construct another copy. I mean, naively, another copy of the what's on the catalytic tape to see if the bits match.
No, you will always, so you will never compress blindly. You always test whether or not you should be compressing first. So once I've tested and said, yes, I can compress, I'm going to take it on faith that decompression will work. Yeah, that's part of this thing that I didn't actually mention. So who here knows some stuff about matching algorithms or whatnot, or graph algorithms in general? So I'll just say, like, I'll toss out a couple of words. And if this means something to you, then it means something to you. And
I don't want to screw up your time.
No, I have truly no notion of how much time I am or not going to use. So essentially, the bootstrapping, okay, well, I'm not going to do it with a marker, so I'm going to say it. The way the bootstrapping from k to k+1 works is you essentially take your undirected graph, and you're going to, it's fine. You're going to take your undirected graph, maybe I'll just move back so we can look at a graph. You're going to take your undirected graph, and you're going to construct what's called a residual graph, which means basically just direct all of the non-matching edges forward, direct all the matching edges backward. And then like add an S vertex over here, which connects here, and a T vertex over here, which connects here. And basically what happens is that every ST path like goes forward along a non-matching edge, backwards along a matching edge, etc. It's like an augmenting path. We've seen this before. It defines the matchings of size k plus 1. It turns out it exactly defines all min weight matchings of size k plus 1. Every ST path of minimum weight defines this, and we had to prove that. But now, the test, how you test whether it's 0, 1, or 2, is you test how many min weight ST paths there are. If there are no ST paths, then the answer is 0. If there's only one min weight ST path, then it's 1. And if there's more than 1, then you're in the 2 case. So that we test that a priori without doing anything to our catalytic tape. Once we know that there are 2 such paths, then we're going to run this compression. And actually, this is exactly why we can do compression and decompression. This residual graph is easy to construct using only the min weight matching of one previous size. And now we just have to, in order to figure out what the weighted edge is, it's basically just some shortest path queries. You check what's the shortest path from S to the front of this, from this to the end, and what's the shortest path from S to T. Because remember, disconnecting this edge doesn't reduce or doesn't increase the size of the min weight path. That's everything that's going on under the hood. The point is, we have a test a priori to know whether or not we're in compression use. And it just so happens to be exactly designed to work in CL and give you the compression and decompression while you're at it. But yes, you never want to compress if you don't know you should, for obvious reasons.
Can you repeat your comment about ZPP?
Sure. So ZPP, the ZPP algorithm for CL is essentially pick a random catalytic tape, run it for polynomial time, and then figure out whether or not you've halted. If you didn't, just return floor. That relies on a randomized, a fact that you can prove that a random catalytic tape runs fast.
Sorry, the definition of ZPP is expected polynomial time or polynomial time?
You can do it either way. So if you want expected polynomial time, pick a random catalytic tape, run it for poly steps. If it hasn't halted, pick a new catalytic tape and do it again. And just do this until it halts. This relies on a fact which I haven't proven here, which is that a random catalytic tape halts in polynomial time. Like any CL machine halts in polynomial time for a random catalytic. The partial de-randomization is, it turns out, we can actually compress every catalytic tape which runs for too long. Like if you run a CL machine and it takes too large of a polynomial time, it turns out I can deterministically compress the catalytic tape I started with. So
I think my question was, you said CL belongs to subclass of ZPP. Yeah.
So this is exactly what I mean. So the subclass of ZPP is specifically the class where I give you I'm a polytime machine, deterministic, not randomized. I get the input. I design a compression-decompression pair. Right? I design 2 polytime algorithms, one which compresses and one which decompresses. I give it to an oracle. The oracle gives me back something that does not compress and decompress. And then, in polynomial time, deterministically, I solve it. So think about it as being like exactly this framework. In this framework, I design the compression and decompression scheme, which work efficiently, and eliminate this success case. Imagine the oracle always gives me a failure case. So because I design compression and decompression correctly, like this random weights thing, I know that if I pick anything that doesn't compress, that I can actually run my algorithm, I can run efficiently. So that's the de-randomization of CL as well. We now have a polytime algorithm which has this compression decompression for the catalytic tape. And now, so ZPP says you pick a random tape, that will work with high probability. This says that all you need to fool is this specific compression decompression pair, and that's enough to run in polynomial time. So what would be a true polytime algorithm for CL? You construct such a string. If you, in polynomial time, with no advice whatsoever, can construct a string that fools the compression-decompression pair, you've got a deterministic algorithm. But for now, all we have is the halfway, which is we rely on some external resource to get.
What complexity class did you say the compression and decompression belong to? Are they like log space?
In our case, they're in polytime bounded CL, but any polytime. Like, if you want to do a partial de-randomization of ZPP, you let your construction of the C and D be polytime, you let C and D themselves be polytime, and you let the post-processing be polytime. But you can study restricted versions of it. So this is a class called lossy code, or a problem called lossy code. But you can have lossy code for some for like, I don't know, NC1 or log space or something. And in that case, you have to construct C and D in log space. Both of them have to be log space machines. And once you give me the string that fools them, I have to solve the function in log space. In my case, all I know is how to do it for polynomial time. But you can study this question at various routes. Actually, a consequence of our result, just because of how everything works out, is that this puts matching in this problem for TC1, threshold circuits. Because it turns out that our construction of C and D is very efficient. C and D themselves are very efficient, and our post-processing ends up, well, maybe post-processing not so efficient, so I actually have to run through every K, but morally speaking, it's, well, actually I can parallelize it, so it's fine. Yeah, so it turns out that this shows such a partial derandomization from randomized log depth circuits to these partially derandomized log depth circuits. Now we have a result that says they are deterministic log depth circuits, right? This recent breakthrough result, which shows that you can solve matching in TC1 or whatever, you should think of it as the full derandomization. I can generate the randomness needed, although they don't do it by isolation lemma, so that's a little bit misleading. No, in general, you cannot still de-randomize isolation lemma, but at least you can like half de-randomize it in the sense of you can witness why it's bad. You know, half de-randomize in this lossy code sense. Yes.
Just to see if I understand. Suppose I give you like a string that has like almost complete algorithm will work. Like
Yeah, the algorithm will just never enter this greater than or equal to 2 case. Like, that seems counterintuitive because it's, it says it's a with high probability statement. So how could it possibly work always with a high Kolmogorov string? And the reason is because of this. Like, if it was a high Kolmogorov string, no such compression scheme could work. Yes. Of note, though, this can work, very low complexity strings can still never enter this compression case, right? All you have to do is fool it. Yeah, and only on this graph. So I make no claims about how random the string you get on your catalytic tape is. I'm not saying because this procedure never compressed that it's random, but it's random enough for us. Oh, this is good. I'm glad that we're going into the details of this. But I guess I'll move on. Reversibility. So the name reversibility suggests maybe the other thing you could try and hope for in such a program, which is that I can do something to my catalytic tape, and then I can somehow like undo it, right? Every step I do has a reverse step. And we are going to focus on a very specific kind of reversibility, which is arithmetic reversibility. So here's my magic setup. Here's what a typical setup would look like. There's some function I want to compute over an input x, and x is given by some subroutine computation, right? So I filled up a whole bunch of memory, and now, I do my subroutine computation, and I gain access to x. Now, x is sitting right there for me, so I'll do some other subroutine to compute f, given it. And then, since f is the thing I wanted, I'll keep it written down in memory. Now I want to be space-bounded, so I'm going to go back and I'm going to erase x. This is like what you think of as a space-bounded subroutine, right? You just kind of leave the memory that's irrelevant off to the side. You do all your work, you erase everything you don't need, and then you continue. We are going to do something slightly more clever. We are going to show that the catalytic tape, or in other words, the full memory alone, is enough to carry out this kind of subroutine. So the way we're going to do it is that we're going to add x to the tape, where add x is no longer like put it there, but it's literally add it. So think of your memory as numbers. X is some number that you can obtain via a subroutine computation. Sorry. And plus x is literally going to be plus x. The memory that's sitting here is no longer going to have anything to do with whatever it was originally or with x. By which I mean, like, if you had one, you could recover the other. But if you have neither, you have no information about what this block is, right? It's completely garbage. Nevertheless, The magic is going to come from somehow extracting x from it and being able to compute f of x anyway. This is the step where all the hard part goes into. Once you have it, you're going to, we want to keep this thing inductively, the same thing should happen at the end as at the beginning. So instead of storing f of x in some extra memory, I'm just going to add it, again, as a number, to some block in memory. And now, what's my cleanup? How do I get rid of x? Well, this is why we went to arithmetic. If I can add x, then surely I can subtract x. Like whatever my program is, just flip all the signs, run it backwards, whatever. Just stick minus signs everywhere that you need, and subtract x. And this allows me to clean up my memory without ever having actually looked at what x was in there. And this allows me to kind of keep a subroutine going. And this seems ridiculous that you can pull this off, but it turns out that this is a very powerful type of subroutine. And now again, there are some simple, nice, clean examples of this. I'm going to give the 2026 relevant one. And this, I should have given citations for all of these. So the matching stuff we saw earlier was work of Aryan Agarwal and myself. This one is due to James Cook and Ted Pine. And this is the notion of a catalytic BFS. So again, we're going to start with a graph. And I'm going to care mostly about like ST paths. And so and I'm going to allocate memory in order to carry out this BFS, not BST. So the way you usually do it, kind of the natural way, is I'm just going to keep track of everything I can reach. Sorry. So what can I reach from S? Well, I can reach S. That's the start point. And then I'm going to sort of, I'm going to work with layered graphs here. I'm going to look at all the edges in the first layer, and I'm going to sort of push all the ones along it. Well, these two edges, since 1 and 2 are 0, like they're not going to push anything along. But since S is 1, then all of its neighbors are going to get this 1 as well. So 3 and 5, I can reach. And then next, I consider every edge in this graph, and I'll just blindly push along all the edges. So 6 has nothing coming in, so it gets nothing. 4 doesn't have a 1, so there's nothing pushed along it. But both 3 and 5 get to push a 1, so the T is a 1, and 7 is a 1. No, let's say that we're doing this in a layered fashion and I know where all the nodes are. So I'm just going to push from the first layer to the second layer, then the second layer to the third layer, and forward. Yeah. Yeah. Let's make things easy. There are reductions. There's an obvious reduction to make a graph layered. It blows up your number of nodes by a quadratic factor. Just clone the graph a whole bunch of times and then put all the edges. Turns out, for time space efficiency purposes, you don't want to do this. Like if you had a linear time algorithm before. But I'm not going to say much about the unlayered case. I'm just going to say that there are still ways to do this. You can, as Sapir says, at every step, push along every edge simultaneously in the entire graph. This incurs some other kind of slowdown, but it's no big deal. Okay, good. So at this point, we can establish whatever we want about the last layer. T is reach, which is what we care about. If you somehow ask me about 6, I could tell you, no, there's no path, etc. We have all the information about connectivity here. And then, once I'm done with this and I've written down my answer, I'm just going to erase everything. Of course, I want to set my memory back to the way it was. Now, how am I going to do this when there's junk? Like, good luck doing anything here. If I add a 1 to this S and then I want to push along all the edges, what am I even going to do? Well, the answer, as I said before, is arithmetic. So let's remove the junk for a second. Let's start over. Let's do almost the same thing. So again, I'm going to set S to 1. And then in my first push, I'm going to push along all the edges. And, I'm going to get all the same values as before. I haven't said anything new. And now I'm going to push in another layer. And suddenly there's a 2 here. Now, why is there a 2 here? It's because I didn't tell you what the push was. Before, the push was an OR. But now, the push is addition. Sorry. So I have this 3 and this 5 both representing a 1. And instead of just taking an OR over all the incoming edges of T, I'm just going to take every edge, and I'm going to add whatever value was before it to the memory spot after it. And the net result of this is it kind of looks the same. You were non-zero if and only if you had a 1 before. Nicely, it also counts the number of ST paths, although you should that should ring alarm bells, because that means that your memory can't get too out of control, because these numbers can get pretty big, but I'm going to sweep that under the rug. Now, what does resetting look like? Before, I just erased everything, and I could still do that, but I can also just sort of unravel what I did, right? I still have these 2 1s here, which is how I got all this information. So I'm just going to subtract, right? Take every edge and push all the values along it again with a minus sign this time. And this exactly puts back all the zeros here for obvious reasons, as does then pushing along all these. So I'm going to work on the layers in reverse order. I'm just going to subtract, and this exactly unravels everything. Of course, I have to subtract the 1 at the beginning as well. All right. Now, what happens when I apply this algorithm with a whole bunch of junk in it? All right, let's get rid of the numbers. This is going to get hairy. This is not going to look too pretty either, but at least it'll be in the realm of comprehension. Tau sub I is going to be whatever value is stored in the ith node before I start my computation. Well, if I want to carry things out as I said, I'm going to start by adding a 1 to S. Good. And now when I add along these edges, suddenly 1 and 2, which played no role before, are going to come alive, right? Whatever values are in there are going to be added along the edges. I don't know which vertices I should and shouldn't care about. So just to be safe, I'm going to add everything along the edges. So register 3 is going to have its tau 3 value before. It's going to have tau s plus 1 coming from this s, and it's going to have tau 1 coming from this 1. Similarly, register 4 is going to get this added this tau 2, and register 5 only has the 1 edge, so it's going to get tau s plus 1. And in one more step, again, I didn't say it's pretty, register 6 is left alone. It has no edges. Register 7 has the 1 incoming edge, but it's going to get added the whole value from before. So this, you look at register 5, it has its own value plus the value that was added to it. The whole thing comes along for the ride. And then meanwhile, for tau t, it's everything coming in. So these are the terms coming from 3. This is just tau 3 plus tau s plus 1 plus tau 1. That's right here. From 4, you get this tau 4 plus tau 2. And from 5, you get the tau 5 plus tau s plus 1. Good. You've added the whole thing along. And you should notice that these plus 1s, if you just ignore the taus for a second, the plus 1s are exactly the plus 1s that you were getting before. So you have the plus 1 from the initial, you have 1 added to 3, 1 added to 5, and you have these 2 1s added to t. So this plus 2. So somehow everything that you wanted to from the pure space algorithm worked, with the only exception being a whole lot of junk. Distinguishing between a plus 1 and not a plus 1, that's not going to work. But nevertheless, this has everything that we want in it. So let's save it for later. We're just going to move it, put it in one free block of memory. It's one number. It's not that much to remember. And then I told you how to unravel the whole process. It works just as well in this case, right? Subtract along the edges. You get the exact cancellations. Subtract and get rid of this minus 1. And, well, how am I going to get rid of all the junk? Well, where did it all come from in the first place? Each of them came from a path in the original graph anyway. I'm going to move the plus 1s up here, and I'm going to notice that each of these taus just came from an addition along an edge, right? So this tau 3 came from addition along this edge, but the tau s also came from along this edge. It just came first from here. And it's all going to work out in exactly the way you expect. So it tells us the obvious way to remove it. Just do the whole procedure again. So without the plus 1 here, I'm going to again push along the edges. I'm going to get all these additions that you had before without the plus 1s. I'm going to get the same thing here. Again, no plus 1s. And, well, you can either do pattern matching or you can just know that what's going to happen at the end. It's going to be exactly the same thing as before without the plus 1s. Which means if I subtract the 2, I get exactly the number I cared about without the obfuscation. And that's the end of the process. sans, of course, resetting everything by one more backwards walk. So what did I do? I walked through the graph 4 times. Once forward, once back, once forward, once back. Only difference between them was a +1 here. And doing this, I completely removed the obfuscation and got the value that I wanted. So this is a very bespoke algorithm for catalytic BFS. Turns out there's variants of it for Savage and whatnot, and there's more general frameworks for computing other kinds of functions. But I gotta say, I really like this. I really like this algorithm. It tells you that what's the punchline? The punchline is that BFS, which takes linear space normally, can be done in linear space where all of it is catalytic. And all the free space that I needed was to remember this one value and maybe where I was in the graph. Do it mod a random prime. Pick a random log n bit prime and do everything mod that. That's all I'm going to say about it. So you get the count of it mod that random prime, but all we cared about was 0, 1. So yeah. Great. And that's our big takeaway techniques. So the last things I'm going to say, and this is again for the people who have endured this talk before, is where are we at now? What is the state of affairs in 2026? And I'm only going to give the highlight reel for the people who are interested in getting into it or who haven't kept up in a little bit. So algorithm side, we have so few lower bounds on this model that you may as well just look for algorithms, because trying to prove that this model can't do something is very, very hard, it turns out. But we have some nice algorithms. So using stuff like what I said before with BFS, you can get fast connectivity algorithms, and using some additional tricks, you can get it for edit distance, longest common substring, Frechet distance, etc. They're not super, super fast. They don't take time m. They take time mn. And they work using very little catalytic space, linear or now even less. You can get slightly sublinear catalytic space, log free space, and still get a very fast algorithm for these problems. Random walks. So random walks can be clearly, estimating random walk probabilities follows from the very first paper because it's a subset of this log depth threshold circuits. But we have, again, more bespoke algorithms now that run very cleanly. Analysis is super simple. Deterministic random walks, I call it. I'm happy to talk about it more offline. This was, I should say, also in the same Cook-Pine paper that had this catalytic BFS. Lovely paper. I said you can do bipartite matching. It turns out using similar ideas, but actually even simplified, you can get maximum matching. You can get maximum matching in general graphs. And this is good because we lost bipartite matching as the nice candidate for why CL shouldn't be in NC2 or something. Now we're still in business. The question of where CL lies is a big open question. It's the biggest open question. We don't know it's in polytime. And now we have candidates for why it shouldn't be in NC. Although we'll see how long that lasts.
It's not in NC just because it's not. This is a matter of data. This is why
you think this is a yeah. This is why I say I have other candidates for what it's worth, but they're a little bit thornier. They're about well, surely you should just write it at this point. Be the change you want to see and whatnot. Yes, hopefully someone proves an alternative version of this result, by which I mean TC. Matrix powering. Matrix powering is a nice subroutine to have. Again, if I want to power matrices, I can actually do it in CL easily. I want to do it very efficiently because it turns out I want to use this as a subroutine. I can save a little bit off of the most obvious algorithms. If you can further improve this, like the efficiency of this paper that I have with Alexeyev et al., please let me know. I care deeply about this problem. Structural complexity. Yeah.
Can you say what is going on here with this matrix powering? Because that's already in TC1, right? So it's just you're getting something better than the general simulation?
Sure. I want to do a log depth circuit where every gate powers a matrix.
I'll ask you after.
The point is I want to do many layers of matrix powering, and The only way I know how to do it is like every matrix powering operation uses the previous one as a recursive call. So if your runtime, yes, it's in CL, but if your runtime isn't very, very good, this scales off too much recursively. We know how to save a little bit in the time. That's it. Yeah, sure. CL is a complexity class. You can study it structurally. Not many questions left here, I gotta say. Pretty much every variant you could think of CL, like slap on any resource you want, and I can show that it's in CL. Like this is a very rare case where non-determinism, randomness, blah, 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 they all don't incur overheads. So admittedly, space is sort of this way. If you go up to P space, right? If I pay quadratically in the, if I pay quadratically, I can capture non-determinism or randomness or whatever. These are in some sense even more efficient than that. You don't pay much of anything in the catalytic space. You pay only a constant factor in the workspace. If your parameters aren't so nice as CL has, then you don't get quite as tight results, but I still have Immermann-Shelop-Shenny, I still have Savage's theorem. Like in every parameter regime, everything we know in the classical world works, but in most of the important parameter regimes, we can say way, way more. We've tried to show CL is in P. We now know that you're going to have to be careful about this. So we have an oracle with respect to which CL equals exp. And not only that, but it's an oracle in a very fair sense. What do I mean by that? Space-bounded oracles are kind of BS, frankly, because you just slap on an oracle tape, which no longer counts as part of your space. The only caveat is you're not allowed to read it. At some point, you just press a button and get the oracle answer out. None of that nonsense. I can prove CL is equal to exp, even when CL is only allowed to make oracle queries from whatever it has written down. So this actually provides a... No, so it's 1 bit output of the oracle. So imagine there's like 1 bit that's set aside on the free work tape. The oracle queries have to come from the input plus the catalytic tape plus the work tape. So there's no write-only separate thing. It's just when I press the button and exactly these tapes are fed into the oracle. And that's nice because if you want to do structural stuff, if you have like a configuration graph and whatnot, there's no hidden dependence on some tape that you can't see. There's no blow up based on the oracle tape. Nothing. Like it works the way you expect it to. So this is actually seems like a pretty annoying barrier. Again, I also have some candidate problems which are going to be hard to de-randomize. The upshot of all of this is that it's hard to say how much easier putting CL in P will be than say putting ZPP in P. Right? You know, it's a strictly easier problem, but it seems like it's not going to be that much easier. You can ask questions about how flexible is the model. If I allow different kinds of resetting, like I only ask you to reset in certain circumstances, or I ask you to reset within, you know, you can make a couple of bits of error when resetting the catalytic tape, or, you know, you reset with high probability, etc. We have a very good handle on it now. For some of them, like for a bounded number of errors in resetting, we have exactly the characterization. For other kinds, we have very, you know, we have like a little bit of slack to get, but that's neither here nor there. New catalytic models. There's other places that use space besides Turing machines, so I'll just mention a few. You know, the quantum group here is technically the ones that invited me, so I'll throw them a bone and say, we do have quantum catalytic space. It is pretty annoyingly behaved because you have to reset every pure state that you could have gotten, or every mixed state or whatever, not just every computational basis state. The resetting guarantee is very strong, which means we have way more structure. Nevertheless, it has already been used in some works that are non-catalytic about understanding like the number of ancillas needed for certain problems. So the definition still has legs. And of course, I showed you this arithmetic reversibility earlier. All of this stuff is like very quantum. So, you know, it was a natural fit for them all. We have streaming now. We sort of always had some notion of streaming, which was like few pass branching programs, but now it's like explicitly studying questions in streaming algorithms, showing that certain time space lower bounds that we have can be bypassed by kind of using enough catalytic memory that you're not going to violate the time space lower bound, but using so little free memory that it doesn't morally mean anything anymore. You know what I mean? Like you need n squared space for this, but you can make it all catalytic. So What does that really mean? Communication, there hasn't been a lot of work here, but it is sort of woven its way throughout a lot of other things like streaming and whatnot. The communication model is, again, a nice way to understand few pass computation. I would like to see more development in this field, but there's still some very solid things that you can say.
You mean communication complexity?
Correct, communication complexity. There is even a small notion of catalytic data structures. Now, this is, you have to be very careful about this setup. I can prove to you some pretty unconditional things about, like, if you just want your data structure to lie in catalytic space, like, no way. But surprisingly, you can actually save some bits of the best data structure by assuming you have a different data structure also on hand. So this paper, which appeared at Fox at the end of last year, kind of, they mention offhandedly that there's a nice little catalytic thing going on. Again, I would like to see more development in this field because there's a lot of algorithmic questions that, you get the upper bound by an appeal to some data structure upper bound. And in that case, I'm not so, such a purist about how your data structure is initialized. I just want you to solve the algorithmic problem with a notion of catalytic data structures. And I'm happy to talk about that offline as well. One last slide. Two last slides. Applications to space. How did you end up down there? That's fine. Ultimately, if all you care about is space complexity, then you care about what this whole setup says about space. And the big thing I said at the beginning was time t in space square root t log t. That was then later expanded to circuits of fan-in 2. And now it is known for unbounded fan-in circuits. So if I give you a circuit of size s with arbitrary fan-in gates, this is still in space square root s log s. Bit of a surprising result. But this follows from a kind of a chain of works that are nice. No.
Just very Boolean circuits of unbounded.
Yeah, think about it as a scaling up of time s. Yeah, so we're really understanding what fits into this model. There might be some restrictions here. I forget. I think it's basically as stated though.
Sizes, gates.
Size is gates. Size is gates. Yeah, size is gates. I think that's right. Size is gates. That's right. Of course, these have to be uniform enough that you know what you're doing in the space. There's some non-uniform version of these, but yeah. This is a result I quite like from last year. There's a whole bunch of stuff using this compressor random framework to understand de-randomization of space-bounded computation. But one, I think, highlight result, there should be some quotation marks here. This is like an instance by instance statement, and there's some more general statements with loss and parameters. But morally speaking, if you give me a graph, I can either estimate the random walk probabilities of it using only non-determinism. This fact is strangely not known unconditionally. Or you can find out connectivity using polytime and only log squared space of memory. Major, major open question. We have the best result we have here when this is poly n is n over 2 to the square root log n. Like, nothing. We basically have nothing. And
because you mentioned that between those two, we think the first one is like complexity theorists use that BPL solves a problem.
yeah, because I guess complexity theorists think BPL is equal to L. So, we believe this. Depends on who you ask if they believe this. I'll believe this for the sake of argument. Why not?
So you're saying it's just at least one of them.
At least one of them is true.
It's instance by instance, right?
It is instance by
It's not
instance.
as strong as
No. I should really have quotation marks here. You can strengthen these and get like you pay, it's not log space, it's like log to the 1 plus epsilon or something like that, or 2 minus epsilon or whatever. You get something of this form actually. That's not instance by instance, but the statement I wrote here is instance.
Somebody comes down and give you, suppose we live in a board that we don't BPL is equal to
Mm-hmm.
Is there anything that this result tells us? Or
No, I mean, as soon as you prove one of these, you don't say anything else. Yeah, so I mean, you could just take this as saying, like, we think this is true, we think this is false, call it. If somehow you thought that this was false, then you have to believe this. Oh, and I guess this is also very constructive, which is helpful, right? This is not some weird non-uniform statement. Some nice open problems for the current year. This one bedevils me, very close to my own heart. Integer GCD and catalytic log space. Very basic primitive, very simple algorithm. I have no clue how to do this. It's very arithmetic. Usually arithmetic stuff we can just knock out of the park. But unfortunately, it's a very linear process. Not linear in terms of the mathematics, but linear in terms of sequential. And that's just a really hard thing for us to handle. Improve the space or time space of a lot of basic primitives like SD connectivity, determinants, etc., using catalytic ideas. So I don't care about proving, some collapse of complexity classes here so much as I say, give me nice algorithms that optimize the space by realizing that some space that you've used in step 1 doesn't have to be set aside for step 2, something like this. We've gotten reviewers complaining that we only have 2 techniques. I think this is BS, but whatever. If you believe, if this reviewer is in the room, then I open the challenge to you to develop a 3rd technique, or prove that somehow everything we can do is the convex combination of compression and arithmetization. Why not? I don't know. I don't even know what that means, but do something. So I'll say the last couple of things. Memory can be used both as a resource for storage and as a resource for computation simultaneously. This is a very nice, clean fact. It seems like a very fundamental fact about space. We've understood this through this lens of catalytic computing, which is our playground for understanding this, but it has led to breakthroughs on stuff like time and space outside of this catalytic model. So it's proved to be not just a very fun playground, but a fruitful one. And I think a nice takeaway is just that we don't know what's going to happen. We got something we expected about time and space, but didn't know how we could prove it by something we didn't even expect to be able to prove. We went the wrong direction on a conjecture. And so I think, there's all these conjectures we haven't even bothered to touch for many years. Whatever, getting NL in space less than log squared n, deterministic or something. We don't touch them. We use them as hardness assumptions. Why not try and prove the other direction at least? Resources, they're both already out of date. This one's much more recent, doesn't matter. Field has moved way too fast since then. But if you'd like to know about the techniques and some of the problems that are still open or stuff that we attempted to solve in the last few years, this is a good techniques paper. This is a good early days of the field paper, defining all the variants, etc. So you can check these out. I'm trying to keep things up to date on my website. I've had this now on my slides for a year. It's needling me. I promise I have the list. I just need to remember how the CSS for my website works in order to put this up on a public sphere. But I want to keep it maintained because I want a lot of people to work on, anything from toy problems to the big killers in the field. So if you want to look at stuff, I do have a bunch up here. But for now, I'll just say that's it. Thanks. Sorry to keep you.
I've got one. So your structural complexities,
Hmm?
you said that you take catalytic log space. That's yeah. So if you had bounded error probabilistic computation, you have non-determinism, you have Merlin interactions, these are all CL. What if you have unbounded error probabilistic computation, or you
Catalytic alternating log space.
what if I have parity quantifier? So
I do not know. Let me think about that. I might know something about it, but I don't think I do. I think that's a good question. Catalytic alternating log space. Alternating log space is equal to P. Naturally, catalytic alternating log space contains P. It's still in ZPP. The way you, we can talk about it offline, but essentially, if you pick a random catalytic tape, it looks like alternating log space. So because you still have a small graph. So I can say something about that, so that's what I can say about that. Naturally, for k alternations, you pay by k log n bits in the free memory, so it sort of interpolates the way you would expect. Parity is a good question.
So what does that mean?
So you would have like an extra witness tape. You want to understand the number of accepting witnesses. It's an odd unit.
Yeah, parity L, but in the CL vault. Don't think that. Definitely has not been brought up in a paper. I don't know if I can conjure something off the top of my head, something that it can or can't do. But is it in ZPP? Actually, most of these things are in ZPP because yeah, it's probably in ZPP because again, pick a random catalytic tape. It's a small graph, so it basically is parity L at this point with some extra names, and parity L is in P. So yeah. Yeah, I mean, that is like that one hammer we know how to hit catalytic with. Pick a random tape. It behaves more like log space than catalytic log space. The only difference is the names. So, yeah. Yes?
So your AC size result that you quoted here at the end, that seems like, well, on the face of it, like it's a big improvement over Williams result because the Williams result, Turing machines, and you're assuming that tape heads can only move linearly from one location to another. It seems like it would probably apply to some random access.
Yeah, that's why I need to be okay. So, why do I have to be especially cagey about this? Because all I know is that it was accepted to Fox and some informal communications thereafter. So I would say wait for the paper by Williams on space to be released to double check what I've said here. Yeah, this is SW down here. This is really bad. It's his undergrad student, and I should know the name, but I do not know it off the top of my head.
So this is not public. This is part
unfortunately, it is only public insofar as the abstract is public. But the paper exists and has been accepted to Fox. So, but maybe not even that. Maybe it's just the title is. Yeah.
If you're the reviewer, you know each.
No. I talked to him. This one's fair game. I have not compromised operational security here.
What it means,
yeah, I have assurances that this is what was said, but this is a game of telephone, so I should be a little bit careful. Yeah. I'm not exactly sure. This S result, this was just presented at CCC last week, and that gets the result for NC circuits. That one I can very clearly claim. That's by Yakov Shalamov. But yeah, this is actually.
Oh, so if it's polyglot depth, then it's.
No, NC size. So I still let you be at whatever depth. Oh, sorry, NC, by which I mean just fan-in 2. So if I give you a fan-in 2 circuit, you can get this savings, no matter what the depth of it is. And that's already something like what you were saying, like more general than time T Turing machines.
Complexity here. Is there a sort of conventional model that captures this?
Oh, like a. Oh, is there like a syntactic model? So I will say that this result was about a syntactic model of like it was like a shared memory model of some kind. Sorry, a non-syntactic model. It's about some shared memory mode of computation, which just so happens to then generalize the result to circuits. But again, maybe there's a caveat here that I'm not that I should be careful about.